Hello everyone, this is Aalelai Vendhan, PhD scholar working under Professor S. Gurunarayanan in EEE department at Pilani, Hyderabad campus. So this video is a part of the VLSI design course in Hyderabad campus in EEE department. So initially we will be covering the basics of Cadence Virtuoso. Like we'll be starting from how you set up the Cadence environment, then how you can design circuits like inverters, NMOS transistors, then measuring their performance metrics. We'll be moving into the DC analysis as well as the transient analysis, and from these analysis, how we can measure power, delay, and so other metrics. Finally, we'll be making the symbols of these circuits. The primary reason for making symbols is like when you're designing a bigger circuit, say adder, full adder. So a full adder will have many gates, assuming AND gate, OR gate, and inverters. So we cannot draw all these gates from the scratch. So if we make a symbol of these circuits, we just need to place those symbols and we can build a higher order circuit. Now we'll move into the tool. This Cadence tool is not available in any of the local machines. So we need to log into the university server for accessing it. The first step is like you need to go to the start menu, then search for the remote desktop connection. So once you find this remote desktop connection, you need to enter the correct IP address for the node which you need to connect. So you will have 4 nodes, namely 172.16.102.245. If you want to work in any other node, the initial 8 digits remains the same. That is 172.16.102. Either you can work in node 245, 246, 248 or 249. All these nodes are under the single server. So as of now, we will be working in 245 node. Give connect. It will ask for a username and password. Everyone will have their own username and password. Okay, so we'll just enter it now. Right, so now we are into the remote desktop location. So the first thing before starting to work into the tool is like you need to create a folder where all your files will be stored. So right click, the same process as in a desktop, just create new folder. Okay, so folder name new one has been created and it is placed in the desktop. What we need to do is Cadence is already installed inside the server, so there is no installation procedure. But this entire tutorial we will be looking to work in the 180 nanometer technology. Those technology files needs to be copied from the server into your own user account. So the first process is copying the technology file from the server into our own user account. So what we need to do is just right click on the folder. There is an option called open in terminal. It is similar to something like the command prompt. So click on open in terminal. Then you need to type this command exactly. So first we'll type the command pwd. So pwd gives you a directory. Like if you can see home/VLSI_lab/desktop/new one. This represents like home is the home folder, home / your user account name / desktop / the folder's name which you have created. Make sure you are always working in the single folder and the same folder which you have initially used. So now we are going to copy the contents. For copying the contents, the command is scp space -r space / okay, so scpr, you're going to copy from one place to another. It's like copying from a source to destination. So the source will be from the server and the destination will be the folder which you have created. So scpr soft / tool _library / cadence _ analog _ labs _ 613 and you need to give a white space. Then slash. Now you need to just enter the exact directory. Like you can refer to the top line where it is written home, your group name, the desktop followed by the folder name. So I need to write home slash VLSI underscore lab slash desktop slash new one. See, one of the important things to note down here is wherever there is a white space, you need to mention it correctly. If you are not giving the white space correctly, then the file contents won't be properly copied. So if you want to check it, just give enter. So now there should be no warnings in this terminal window. So we just need to wait for maybe a couple of minutes because the entire 180 nanometer technology files needs to be copied into our own folder. Within, maybe if you're accessing your folder within 2 or 3 minutes, sometimes those files may not be copied. Yes. So now if you open the folder, you can see another subfolder created called Cadence Analog Labs underscore 613. So if you have followed the procedure correctly of installing 180 nanometer into your own working node, then this folder should have appeared here. Fine. Now you can close the terminal. Okay. So if in case, as I was telling before, if the entire thing has not been copied, then this warning will appear like there's a process running it. Still, do you want to close it? So we'll just wait for some more time before the process ends. So the process running in the background. There are two terminologies we need to know before working into the Cadence. One is called library, the other is called cell view. So typically a library means a folder in a desktop. So library in Cadence refers to a folder. A cell view refers to a file. So it's like you can have multiple files inside one folder. So whatever circuit we are going to design, we can assume the first circuit is called NMOS 1, second circuit is called PMOS 1. So all these will be under the category cell view. And all the cell view should be under the same library, right? So now it is done. We are closing it. Now again open the folder which you have created. Don't open this folder. Instead, right click. Again click open in terminal. Okay, now we are going to invoke Cadence and we will start working on it. The command for invoking it is virtuoso, virtuoso space ampersand. So click enter. Okay, so this is one typical warning which we can see. So it is telling true color is not supported. So what we need to do is just log out from your account. So before logging in, there is an option called show options. Just click it, and under show options there's something called display. In display, make sure the colors is in true color 24-bit. So change this to true color 24-bit. Now click connect. So again the same credentials. Right. So we'll go to our folder, right click, open in terminal. So virtuoso ampersand. Yes. Now it's opening. So you can see at the bottom there is a log window. This is called the Cadence log window where all your warnings, errors, whatever operation we are performing on Cadence appears here. Fine. So never close this terminal without exiting the virtuoso. If in case you close this terminal, it is indirectly you are exiting out from all the application. So if you want, you can close the folder but not the terminal. You can minimize the terminal. As I told, first we need to create a library. Then we'll move into the cell views. So go to file, new. There's something called library. So click on it. So we can give any one. So I'm giving LIB, the name of the library. On the right hand side, you have many options like compile and ASCII technology, reference existing libraries. The option which you need to select is the third one, attached to an existing library. The reason is we have already copied 180 nanometer into our own account. So we need to attach the library which we are creating with the 180 nanometer. Attached to an existing library, click OK. Then it will ask which library we are going to attach. That will be the GPDK 180. Click GPDK 180. Done. So you will get a message at the log like design library LIB successfully attached to technology library. So our user defined library has now been attached to the existing GPDK 180 nanometer library. Next, we will move into the process of cell view creation. Same, go to new, go to cell view. So here, make sure you have the library is the one which we have created. We have created in the name LIB. So give the name LIB. Then in the cell you can give. So now initially the experiment will be based on the NMOS characteristics. So we will be finding the transfer characteristics of NMOS like VGS versus ID. So I will give NMOS char, NMOS CHAR. So the view will be in schematic and click OK. So this is like the licensing warning. So you can just click session and it goes off. So first we have created a library called LIB. Once the library is created, we are going to create a cell view and that cell view is named NMOS char. Make sure the cell view which you have created is inside the library which you have created. Fine. So the first thing is we need to going to find the transfer characteristics. So if we remember the components needed for this are, you will have an NMOS transistor, 2 voltage sources for VGS and VDS, and you will need a ground. Fine. If you look at the top toolbar, you have something called create instance. So click that create instance. Then it will ask go to the browse. So that all the transistors are in the 180 nanometer technology. So you need to go to GPDK 180 in the library. Then again you have various NMOS, NMOS 3, NMOS HV. So as of now we will use a 3-terminal NMOS wherein the substrate is indirectly connected to the source. So click on the 3-terminal NMOS 3, click on symbol, and if you just hover around the workspace of the schematic, you can see a transistor appearing there. So just click it once, click escape. The thing is, whenever you are performing any operation like creating a symbol, creating a instance, copying a wire, if you're done with that operation, make sure you give escape, or else the same operation will continue. Your mouse pointer won't change to a normal mouse pointer. Fine. Now again I'm going to create instance. So all the voltage sources, ground, capacitors, resistors, all your components will be under the library analog lib. Now go to analog lib. So we'll need just 2 components. One is a voltage, DC voltage source followed by a ground terminal. So ground will be under the category GND. So you can see GND. Just place it in the schematic as of now. Now again go into create instance. Now move into the VDC at the last. Yeah, you have VDC here. So you'll need 2 voltage sources. One gate to source, one drain to source. Fine. Now again we'll give escape. So all the components are placed now. The next thing is you need to connect all these components together. Fine. So just press the letter F. F is the shortcut for fit screen. Or if you want to check it out from the top toolbar, there is an option called zoom to fit. Okay, you can give zoom to fit. So your ground will be here. So this voltage source will act as VGS. This will act as your VDS. Fine. Now for creating a wire, again refer to the top toolbar. There is something called create narrow wire. Okay, click that. So positive terminal of voltage source to gate, this one to drain, and the negative terminals will be grounded. Fine. Now the connections are done. By default, the transistors will have a width of 2 microns. Okay, but our entire experimentation will be having a fixed value of 400 nano. If in case it has been mentioned to use a different value, you can proceed and use it, or else it is better to maintain the width of the transistor as 400. What we need to do is, if you want to alter the properties of any component, transistor or voltage source or anything, just click on that component, press Q. Okay, Q. Once you click Q, the properties will automatically appear, and here there is something called total width. So change the total width to 400 N instead of 2U and click OK. Now you can see earlier it was 2 microns, now it has become 400 nano. Right. Before running the simulation, we need to give the voltage sources. For 180 nanometer technology, we need to give the voltage values as 1.8 volts at the max. Okay, again click the component, press Q, properties will open, DC voltage value 1.8, done. Again 1.8, done. So now we can see our transistor has the length of 180, width of 400, and your VGS is 1.8, your VDS is also 1.8. So all the connections are done. So before proceeding, there is an option called check and save. Again, the toolbar at the top, there is an option called check and save. Click it. If in case there is any warnings, errors or anything which are not logical, okay, logical will be related to your connections, but if you have forgotten any connections or if there are any double connections between two same nodes, all these things will appear if you give check and save. So as of now we don't have any errors, or else errors or warnings will pop out if you give check and save. Fine. So now we are done with designing the NMOS transistor. Now we will move into the simulation part. Okay, go to launch. Okay, click the option ADEL, Analog Design Environment L. Fine. So we will go to ADEL. Again it asks the same warning, just click session. So whenever this licensing warning occurs, you need to click session and it will go off. Fine. Now you need to give the settings for getting the output. Like you're going to give the inputs and you'll get the outputs. The tool will give you the outputs. So initially I told we are going to plot the transfer characteristics. So transfer characteristics literally mean VGS versus ID, the drain current. So what I'll do is there is something called analysis. So you go to analysis, choose. We are going to do DC analysis now because all the voltage sources are also in the DC form. So click DC, click save DC operating point. Now while plotting the transfer characteristics graph, we know that ID will be in the y-axis. So x-axis you will have VGS. While choosing the analysis, we will choose which will be taken as the input. Fine. So we need to click the component parameter here. Then it will ask against which input component we are going to get the output. So go to select component, choose this voltage source because this is your VGS. Choose it. You choose I want the voltage because it will have many other parameters here, magnitude, phase, imaginary components and everything. But we are only looking at the DC voltage. Now click OK. So again go back to your analysis. You can see V0. V0 is nothing but the voltage source name. The DC voltage VGS name is V0 in this tool. Fine. So you have selected DC voltage, clicked save DC operating point. Then you have checked in the component parameter. The last thing is between what values you are going to simulate. So the maximum value of VGS as mentioned is 1.8 and the minimum value is we can start from 0 and we will move till 1.8. Fine. Now click OK. So if you see in the ADE, you can see something called analysis. So this is what you have set now. So from voltage 0 to voltage 1.8, you are going to vary a VGS and you are going to plot the output. So now we know the output is ID. For the tool to understand, there is an option called outputs. Go to outputs, go to be plotted, select on design. Make sure you just click only the drain terminal of the transistor and not the wires or the entire transistor. If you click the entire transistor, all the 3 terminals will be selected. Okay, make sure just click this red colored box which is the drain terminal of NMOS. Done. If you go here, you can see NM0D. NM means NMOS, 0 means the 0 transistor. NM0 is the name of this transistor and the drain terminal. Right. So now we have set the inputs. The VGS is the input and we have also set the outputs. Fine. So the last we need to run the simulation. So click run simulation. Yes, now you can see a graph right? So it is starting from 0 and it is going up to 1.8. I think these are all appearing as dots. Okay, if you want to increase the intensity of this image, double click on the graph. So it will ask what type of line you want. So you can go for solid. Instead of fine, you can go for medium and click. Okay, so now it is visible. Fine. So from the transfer characteristics graph, the one thing which we can observe is the threshold voltage, right? So threshold voltage appears somewhat here. So it's somewhere around 0.45 or 0.43, right? So now we have plotted the transfer characteristics and we could see the VTH is somewhere lying around 0.43 to 0.45 volts. Fine. So this will be the DC analysis part. Okay. For the AC analysis part, we need a circuit instead of a standalone transistor. Fine. So what we will do is, for creating a new circuit, fine. First thing is you will close the existing windows. Right. Now again the same initial process. You don't need to create a library because library acts as a folder inside Cadence. The library will be same. You will create a new cell view only. Now we are going for the transient analysis of an CMOS inverter. Fine. What we will give the name as INVER. Okay, inverter. Inside the same library. Okay. Last time when we were creating the NMOS design, we just used only one transistor. But as it is an inverter, we need both NMOS as well as PMOS. So first we'll go to GPDK 180, follow the same process. So there's an NMOS 3, we'll click that, we'll place the NMOS here. Fine, again go to the library. Now choose PMOS 3. Fine. So for inverter, you need an NMOS and an PMOS. So we have placed both in our schematic workspace. The other things are, as this is a transient analysis, last time we had DC sources. This time you will have AC sources. So go to analog lib, or to be precise, instead of an AC source, it should be a pulse waveform. Instead of VDC, you will go to the V pulse. Yeah. So you will have only one voltage source. There is no VGS or VDS. So it's just a single voltage source. Followed by, you will have your ground terminals. You will have your ground. But there is one additional component which we need to add. So you may follow the same practice for all the circuits hereafter, because hereafter it will be combinational, sequential. For any circuit, you will have something called VDD, the common power supply, right? So how we can create VDD is, you again have a source called VDD. So you place this VDD because the VDD will be connected to the source of the PMOS transistor, right? Then this VDD needs to be fed with an value which is 1.8. So again place the same VDD symbol, and this 1.8, as we know, is a DC power supply. So place this VDC here. Again, a shortcut for copy is C. So the shortcut for copy is C. For opening the properties of any component is Q, and for fitting the workspace to the window size is F. Right? Here you can see this VDD now is a standalone symbol. It's just a symbol which gets the value from this voltage source, which is a DC power supply. Again, we need to change the properties. We'll go to properties. This value is 1.8 volt. Fine. Now we can realize that this VDD gets 1.8 volt because of the circuit which we have created here. Okay. So irrespective of your circuits from here on, be it sequential or combinational, you will have an VDD. So once you have this VDD placed, you need to give such a configuration, or else your VDD won't have any value and the circuits won't run. Fine. Now we will move to the connections. So connecting VDD to the source of PMOS, shorting the drains of both N and P. Then this will be going to ground, and your voltage source negative terminal to the ground, positive terminal to both the gates of NMOS and PMOS. Fine. Again, the properties of both MOSes. So the width should be 400 nano. Here also the width should be 400 nano. Fine. So now we are done with the basic connections. The only thing which we have not mentioned here is the how do we set the input voltage source. As it was a DC voltage source, it was easy, like we will give 1.8 volt and it will be done. But now we are going for the AC analysis. What we need to do is click Q. First thing is from which value of voltage we want our waves, input waves. So 0 to 1.8. So that is fixed. Then we need to mention the period, rise time, fall time and the pulse width. Assume we'll have a period of 2 micro and pulse width is 1 micro. So I am having a 50% duty cycle. Then you can have a rise time of 1 nano and a fall time of 1 nano. Done. So you need to have 5 parameters. You need to enter them. One is your voltage value, time period, pulse width, rise and fall time. Done. So click OK. Fine. When we are in the last experiment of a DC analysis, you are going to measure the current from ID. That's it. But here you are going to check the input waveforms and output waveforms. As it is an inverter, we will check whether the output is an inverted form of an input. So we know that the input is from this voltage source and output will be taken from the drain terminal of both these transistors. So instead of clicking these wires during the analysis, we can have pins. Pins are nothing but you can use them to label the inputs and outputs. So assuming the input is Vin, okay. So the direction by default is input. So if we want to create an output pin, we should change this direction to out. So by default direction is in. So we'll place the pin here. Now we need one more pin. I'll name it V out for the output. So we'll place it exactly at the center. Fine. Give escape. Now using wires, connect these input and output terminals. Fine. So now our entire schematic is done. We have a VDD whose value is supplied here. Then we have an inverter connections where 2 drains are shorted and PMOS source is connected to VDD, NMOS source is connected to ground and both their gate terminals are shorted while giving an input value which is an AC signal. Finally the output is taken from drain terminals. Fine. The same procedure, go to launch, click ADEL. So the main difference is last time the analysis was DC analysis. Here by default it will be in transient analysis. Fine. So if you remember, the period was 2 microns and pulse width was 1 micron. Make sure your stop time is always greater than your time period, or else the entire cycle won't be visible in the waveform. Fine. Now we will give 10 micro. So from 0 to 10 microns I'm going to analyze. Fine. So that the input we have taken as VGS, where what we will do is we will go to the same thing, analysis component parameter. But while performing a transient analysis, both your inputs as well as your outputs need to be defined from the output column. So go to outputs, to be plotted, select on design. So the first thing is you need your input, your output. Fine. So you have selected your input and output where you can see V in and V out. Fine. The last step is you need to run. So both the graphs are in red color, so it's not visible. What we can do is we can again change the properties of one graph, double click on it, can change the color to maybe green, and instead of a dot make it solid and make it medium. Fine. So actually both are superimposed over each other. What we can do is there is an option called split strips, split all strips at the top toolbar. Just give that and all the strips will be split, and again we'll also make this a solid line. Fine. So V out, the top one is your output, V in is your input. You can see here a single input cycle is from 0 to 2 micron. So initially it goes to high from 0 to 1, and from 1 to 2 it goes to low. So the generic property of an inverter is when your input is high, your output will be the opposite, which is low, which we can clearly observe here. So whenever the input is high, your output becomes low, and when your input is low, your output becomes high. So far we have seen how to create an NMOS transistor, then find its transfer characteristics using DC analysis. Next, we created an CMOS based inverter, how we will give the inputs, then using transient analysis, how we were able to check the working of the inverter, right? So the next part will be measuring the metrics. So there are two metrics particularly for two primary metrics, particularly for any circuit. One will be the power, other will be the delay. So initially we will see how to measure the power. So we can close this graph. There is something called outputs. Again, we need to go to outputs. Go to the last option, save all. Okay, go to save all. Then there is an option called select power signals to output. By default, everything will be in switched off mode. You need to give all. Okay, select power signals to output, select all, click OK. Now again rerun the simulation. So once you get the output waveform and check whether the validity of the circuit, go to Tools, Results Browser. So Tools, Results Browser. Now go into your waveform window. You can see all the results browser in the left hand side. Okay. Go to this tran, double click and open it. We are going to find the average power. So this average power component will have static, dynamic and leakage. Okay, what you need to do is click power, right click on it. Then there is an option called calculator. Okay, right click the power, just press calculator. As it is an average power, you select the function average. At the bottom, you will have the entire functions from mathematical, delay, rise time, fall time, all the functions are there. You need to click the function average, then click apply. So here we can see the formula average of power from the result of transient analysis. So we have performed a transient analysis wherein we have a component PWR and we are going to measure the average of that. So there is an option called evaluate the buffer. Click evaluate and you can get the average power. So it comes around 14 nanowatts. So for running 0 to 10 microwatts for a CMOS inverter with the specification of W as 400 nanometer, you will have 14 nanowatts. Fine. Now moving into the second component, which is the delay. So again split your graph strips. So from this solid, make it to solid lines. Fine. So the easiest way of measuring delay is like you can use a calculator. What we need to do is again go to tools from the waveform window. There is the option calculator. Go to all functions. Last time we had used the function average for measuring the average power. This time we will go to the function called delay. Just click delay. There are two signals. So you are going to find the delay between output and input, right? And the delay, as you know, has two components, TPHL, TPLH, high to low delay, low to high. So first we will measure the low to high delay. So the first signal will be just keep your cursor in signal 1, directly move to your graph and press the Vout waveform. You can see the Vout signal comes here. Again, delete everything in signal 2. Keep your cursor in signal 2. Move to Vin waveform and click Vin. Done. The threshold value by default will be your half of your voltage, input voltage. Like you are given 1.8. So 1.8's half value is 0.9. So by default, threshold voltage value will be taken. And again, edge numbers. So before talking about edge numbers, we will keep the edge type in either. Okay, keep the edge type in either. So coming to edge numbers, what are them? So if you can see, this is edge 1 of output, edge 2 of output, edge 3 of output, edge 4 and so on. And for input, this is edge 1, edge 2, edge 3 and edge 4. Now we have specified the edge number as 1 and 1. So the delay will be computed between this edge and this edge. So edge number is 1 and click apply. Again click evaluate the buffer. So we have a negative delay in the sense we need to reverse the signals. So it comes around 75 picosecond. Next, this will be your TPLH because your output is TPHL. Your output is falling from high to low, whereas your input is going from low to high. Now we'll go for the other case, TPLH. For TPLH, just change the edge number to 2. That's it. Because while measuring the delay between these two edges, we can get the other component of delay. Give apply, evaluate buffer. So you have something called 55 picoseconds and there it was 75 picoseconds, right? So now we designed a CMOS inverter. Then for that inverter, we have measured the power and delay. So power was something in the 14 nanowatts and delay had two components, which was 75 picosecond and the other was 50 picosecond. Then by using the mathematical calculations, we can find the average propagation delay, right? So now moving into the last part where we are going to create a symbol. So before creating a symbol, the important thing is you need to remove all the sources, be it current source or voltage source from the schematic. There are two sources. One is your input Vin and the other is your VDD. Fine. So first, just select this entire thing, click delete. Done. Now delete all the sources and also the extra wires. So for deleting it, just click the corresponding component or the wire and press the delete key. Fine. Now click check and save. Here also you should not get any warnings or errors, so that if any warnings or errors occurs at this stage, then though your symbol will be created, it will cause issues in the larger schematics where these symbols will be used. Fine. What you need to do is go to create. There's an option called cell view. Go to create and cell view. From cell view. So the library name by default will be the library which you have created. Cell name will be your file name. And you can see here from schematic to symbol. So as of now, by default, this is a schematic and you're going to convert the schematic into a cell symbol. So click OK. Then you can have your pins at any direction, left, right, top or bottom. But by default, we have the input pins on the left side and the output pins on the right side. Fine. So your input pins are Vin and your output has only one pin, which is Vout. Click OK. You will get a new window, which is the symbol window. Just delete this instant name and the red colored box. Fine. Okay. So you can see your left hand side you have the Vin, right hand side you have the Vout. So this is your input, this is your output. But this symbol should have a name, right? So we'll just name it invert. So now we have created a symbol of the inverter, and this symbol can be used for multiple circuits. Okay, just click check and save. See, the usage of symbol is so easy that here we have a transistor, right? So this transistor can be used in any schematics. Similarly, this entire symbol will now appear in your instance column. You can check that. We'll go to new cell view. This cell view is just for placing the symbol which we have created. Okay. Now go to create instance, browse. This is the library which we have created, lib under LIB, we have created the symbol of an inverter. That cell view name is INVER. Here you can see there is a symbol. So if you hover around the schematic, so just like how you place any component inside the schematic window, now the circuit, like the inverter which you have created, is itself converted as a component by the means of making it as a symbol, right? So by this way, if we are designing larger circuits, we can use symbols instead of designing them as transistors in a standalone fashion. Fine. In the second part, we'll be looking into the layouts, how we'll convert the schematics into layouts in Cadence. Thank you.